Welcome to the HESI A2 Test Prep Online Lesson Series. In this session, we'll go over the math section of the HESI test. In this video, we'll cover 16 math questions for your HESI A2 Test Prep. We'll cover absolute numbers, rational and irrational numbers, square roots, cube roots, scientific notation, and factorials. Before we start, make sure you have a pencil and paper so you can take notes and follow along through the problems. Then download the Test Prep app from the App Store or Google Play. It has homework and practice tests to support this lesson. The app also has a prediction test so you know exactly when you're ready to take the real test. Question 1. A equals the opposite of the absolute value of -3 minus the absolute value of -12. So what these absolute values are going to do is make anything inside of them positive. So this -3 is going to become a +3. This -12 is going to become a +12. So if we rewrite this, we end up with a minus +3, which is just -3, and then minus 12. -3 minus 12 equals 15, -15. And now the question is asking us, what is the opposite of the absolute value of -a? So a is just -15. We have a negative in front of it, so negative. And then we have a negative outside of our absolute value. We have a negative and a negative here, which is going to make a positive. So we have absolute value +15, negative outside. That 15 is already positive, so our absolute value signs are going to drop away without doing anything. And we're left with -15. Question 2. In the sequence above, continues as shown, what is the sum of the first 66 terms? So let's take a look at the sequence. We have 1, 2, 3, 1, 2, 3, 1, 2, 3. And we know that there are going to be 66 terms. So if there are 66 terms and we have this repeating pattern of 3 terms, we can find out how many times this pattern is going to repeat by dividing 66 by 3. 66 divided by 3 is 22. So this pattern of 3 numbers will repeat 22 times. Now the question is asking what is the sum of those 66 terms. So let's find the sum of each individual pattern, which is 1 plus 2 plus 3, which equals 6. And then if that 6 is repeating 22 times, we have 6 times 22, which equals 132. Which of the following is not a rational number? So let's start by defining a rational number. A rational number is an integer divided by an integer. And then recall that an integer is just a counting number. So for example, 1, 2, 3, 4, or -1, -2, -3, -4. These are all integers. So let's see if we can represent the numbers that they gave us in terms of an integer divided by an integer. 1 over 2. 1 is an integer, and 2 is an integer, so 1/2 is good. That's a rational number. 0.38 repeating is a little tricky, but we have this trick here. Whenever we have a number repeating, in a decimal place, what we're going to do is identify what place this is. This is the hundredths place. So we're going to make a 99 here. It's always going to be a 9 if we want to create a repeating decimal. This is just a math trick that you'll have to take my word for at the moment. So that's going to be 38 divided by 99. You're more than welcome to check that with your calculator. 38 is an integer, 99 is an integer, so 0.38 repeating is good. Square root of 64 equals the square root of 8 squared, right? Because 8 squared is 64. These cancel out, and so the square root of 8 squared equals 8. And whenever we have a whole number, we can always write it as a fraction by dividing by 1. 8 is an integer, 1 is an integer, so that one is good also. So all that's left is pi. Pi repeats forever, 3.14159, and there is no pattern. There is no distinguishable pattern. This will go on infinitely. And there's no way we can represent this with an integer divided by an integer. Which of the following is not an irrational number? So let's take 169, right, because that's inside of each of these roots. We might know that 169 equals 13 times 13. So we can write 13 times 13 equals 169, or 13 squared equals 169. All right, so remember when we're dealing with roots, the number outside of the radical tells us how many of the same number we need to be able to take that number outside of the square root. So for example, if we look at this first one, the fifth root, we would need 5 of the same numbers. So for example, 2 times 2 times 2 times 2 times 2, that would be 2 to the 5th. And then because we have 5 2's, we could take that 2 outside of the square root. If we can't do that, if we're left with a number inside a radical and we can't take it out, that will always be irrational. So if we have 13 squared inside a radical, we have a 2 here, right? 13 squared. The only way we're going to be able to take that 13 out is if it's a square root, which equals 13. This is the only rational number. And then important to know, if you don't see a number outside of the radical, it's always a 2. Right? So if there's no number there, it's a 2 by default. And that's what we're going to see most of the time in math. We're dealing with square roots. Express 3.75 million, or express 3,750,000 in scientific notation. So scientific notation is a notation we use for really big numbers and for really small numbers. We want our decimal to have only one number to the left, so in the ones place. So in this case, it would be right here between the 3 and the 7. So the 3 would be the only number to the left of the decimal. Now, how many times are we going to have to move this decimal to get there? It's going to be 1, 2, 3, 4, 5, 6 times. So we're going to have a 10 to the 6th, and that's going to be 3.75 times 10 to the 6th, because when we move the decimal, we have 3.75, and then all of those zeros after the 5 drop off because they don't mean anything, right? 3.75 is the same as 3.750, which is the same as 3.7500. All of those extra places are empty, right? There's nothing there. If we put a 0 in the thousandths place right here, there's nothing there. It's an empty place, 0 thousandths. So our answer is going to be A, 3.75 times 10 to the 6th. All right, here's a case where we have a very small number that we want to represent using scientific notation. We'll do that by moving our decimal right here between the 4 and the 5, so we only have one number to the left of our decimal, which is the 4. How many times do we need to move the decimal to get there? 1, 2, 3, 4, 5, 6. And in this case, we moved our decimal to the right, so it's going to be negative. Our exponent is going to be negative. So we'll rewrite that number with the decimal moved, 4.5, 6, 7, 8. Nothing gets dropped off here because these are all numbers, like these are all values, all the way down to the 8 in that 10 thousandths place. And then times 10 to the negative 6. Calculate and express the result in the scientific form. So this might look intimidating. We have a lot of zeros here, but we can make it easier on ourselves by just focusing on this 32 and this 54. We're going to do 54 times 32, and then we're going to worry about all of those zeros later. 4 times 2 is 8, 5 times 2 is 10. We're done with the 2, add a 0. 4 times 3 is 12, carry the 1. 5 times 3 is 15, add 1, 16. Add these together. 8 plus 0 is 8, 0 plus 2 is 2, 1 plus 6 is 7, and bring down the 1. Right, so how many zeros did we ignore? 1, 2, 3, 4, 5, 6. We're going to tack on all of those zeros. 1, 2, 3, 4, 5, 6. And then how many times did we need to move the decimal to make this 32? Right here, to make this 32. We moved it 1, 2, 3, 4, 5 times. So we're going to move this decimal 1, 2, 3, 4, 5 times. So we end up right here. So that was not scientific notation, just so we're clear. That was just a trick for multiplication to make this problem easier. Instead of writing out all of these zeros, we ignore them and then we account for them at the end. Right? If we have zeros to the right of a number, we just tack them on like we did. If we had to move the decimal to the right to turn a decimal into a whole number, then we're going to account for that by moving the decimal in our answer to the left, the opposite of the direction we used to make that 32 in the first place. 17,280, and we want to express this in scientific notation, which means we need the decimal to be between the 1 and the 7. That way the 1 is the only number to the left of the decimal. So we're going to move this 1, 2, 3, 4 times to the left. So we have 1.728, that 0 drops off. And since we moved the decimal to the left, our exponent here is going to be positive. So it's going to be positive 4. Question 8, simplify the square root as much as possible. So we'll start by breaking down 75. What times what equals 75? 3 times 25. 3 is a prime number, it can't be broken down, so we're going to move on to the 25. 5 times 5 is 25. right? So this tells us that 3 times 5 times 5 equals 75. So we can rewrite the square root of 75 as the square root of 3 times 5 times 5. Right, and remember there's nothing outside of the radical, so it's a square root. This is a 2, just an invisible 2 here. 3 times, and then another way we can write this is 5 squared. Right, we have 2 5s here, so this 5 is actually going to come outside of the radical. It's going to come outside. So 5, and then there's nothing we can do with that 3 because there's only one of them. So the 3 stays inside and we're left with 5 square root of 3. Question 9, simplify the square root of 169 y squared. So you might know that the square root of 169 is 13, right? So 13 times 13 equals 169. And then y squared can be written as y times y. We can rewrite this whole thing as 13 squared times y squared. And that means we can take out a 13. It's going to come outside. And we can take out a y squared. So that's also going to come outside. So we're left with 13y. And then nothing's inside the square root, so it just goes away. So final answer is 13y. Question 10, solve 4 times the square root of x equals 56. So 4 times the square root of x equals 56. As always, we want to get the x by itself, so we can start by dividing both sides by 4. These cancel out. The square root of x equals 56 divided by 4, which equals 14. And then, because this is a square root of x, we're going to undo it by squaring it, right? The square root is the opposite of the square, and they cancel each other out. So that leaves us with x. Because we squared the left side, we also need to square the right side. And 14 squared is 196. You could always check that by stacking and multiplying. Just like this. Determine the cube root of negative 512. So first let's break down 512. 2 times 256 equals 512. 2 times 128 equals 256. 2 times 64 equals 128. 8 times 8 equals 64. And just because I'm running out of space, I'm going to write it like 2, 2, and 2. Make 8. 2 times 2 times 2 make 8. So these are our prime factors of 512. Don't worry if it takes you a little longer to do this, as long as we get there in the end. So we were doing 2 times 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 2. And we should have 9 2's here. Yep. So that matches up with what we had, because all of these 2's multiply to make 512, And then don't forget we have a negative out front, so we'll put that right in here. And this is a cubed root, which means we can take a number out if there are 3 of that number. So we have 3 2's, 3 2's, 3 2's. That means we can take out a 2, we can take out a 2, and we can take out a 2. So for each set of 3 2's, we can take out 1 2 because this was a cubed root. So that cubed root is telling us we need groups of 3 to be able to take the number outside of the radical. So we have 2 times 2 times 2, and then don't worry about having a negative in the radical for now. Because it's a cube root, that's just going to come right outside. If it's a square root, it becomes a little more complicated, but that's a little bit beyond the scope of this test. Negative 2 times 2 times 2 is going to be 8. Negative 8. Question 12. Solve the cubed root of y plus 10 equals 12. Cubed root of y plus 10 equals 12. We're going to start by subtracting 10 from each side to get that cubed root of y by itself. So 12 minus 10 is 2. Now, just like before, when we wanted to get rid of a square root, we squared. Now we want to get rid of a cubed root, so we're going to cube both sides. So cube that and cube that. These cancel out. We're left with y here, and then 2 cubed equals 2 times 2 times 2, which equals 8. Question 13, evaluate the expression 6 factorial divided by 4 factorial. So factorial just means that we're going to multiply 6 by every integer less than 6, ending with 1. And then same with 4. So 6 factorial simply means 6 times 5 times 4 times 3 times 2 times 1. And then we're dividing that by 4 times 3 times 2 times 1. We see that we have some similar numbers in the numerator and the denominator, so we can cancel them out, right? So we can do that because we're basically dividing by each of those numbers. So ones cancel out because ones don't change anything, and then I could divide the top and the bottom by 2, or I could just cross out the 2's. I could divide the top and the bottom by 3, or I could just cross out the 3's. And I could divide the top and the bottom by 4, or just cross out the 4's. That leaves me with 6 times 5, which equals 30. Question 14. How many floorboards 2 1/4 inches wide are needed to cover a floor 15 feet wide? So we have inches here and we have feet here. So we're going to need to change either inches to feet or feet to inches. That way we have 2 numbers using the same unit. Either would work. I'm going to change feet into inches. So we'll do 15 feet times 12 inches. Real quick, let's do 15 times 12. 5 times 2 is 10. 1 times 2 is 2 plus 1. It's 3. Done with the 2, done with the 1. Add a 0. 5 times 1 is 5. 1 times 1 is 1. Add them together, and we have 180. So this is 180 inches. So that's the width of our floor. Now we're asking how many floorboards, which are 2¼ inches wide, would need to cover all of that 180 inches. So like before, we're going to want to turn our mixed number, that 2 1/4, into an improper fraction, just because improper fractions are typically easier to work with, especially when we're talking about multiplication and division. So we'll do 2 times 4 is 8. 8 plus 1 is 9. So 2 1/4 equals 9/4. So we know that these boards are 9/4 of an inch wide, and we want to know how many of these we need to cover an entire floor, which is 180 inches. So how many floorboards times one floorboard is going to equal 180 inches? We're going to solve for x by dividing by 9/4 on both sides. These cancel out, leaving us with x equals 180 divided by 9/4. When we divide by fractions, we keep the first number, 180. We change the division to multiplication, and we flip the second fraction. So keep, change, flip. All right, we know that 180 is the same as 180/1. We can always turn a whole number into a fraction by dividing by 1. And then I'm noticing here that we have 180, which has an 18, and we have a 9 in our other fraction. So 18 and 9 can both be divided by 9, right? 18 divided by 9 would be 2, and then we have that extra 0 there, so that's 20. And then 9 divided by 9 is 1. Now we're multiplying fractions, so we just go straight across. 20 times 4 is 80. 1 times 1 is 1. So our answer is 80/1, which equals 80. 80 floorboards. Question 15, if a 2-pound walnut pack costs $38.40, what is the cost of a 6-ounce pack at the same rate? So we can change those 2 pounds into ounces, or we can change those 6 ounces into pounds. Either would work. In this case, I'm going to change the 2 pounds into ounces. So 2 pounds. We know each pound equals 16 ounces. Therefore, 2 pounds is going to equal 32 ounces. Now we can find out how many dollars each ounce costs by dividing $38.40 by 32 ounces. So we're going to do 38.40 divided by 32 ounces. So this would be dollars per ounce. We're going to need to long divide. So 38.4 is being divided. That's going to go inside of the box. 32 is doing the dividing. That's going to go outside the box. 32 does not go inside 3. 32 goes inside 38 one time. Subtract, and we have a remainder of 6. Bring down our 4. 32 goes into 64 twice, exactly 2 times. 2 times 32 is 64. Subtract, 0 remainder. Move our decimal up here, and we find that it's $1.20 or $1.2 per ounce. We're asking what the cost is of a 6-ounce pack, so we're going to do 1.2 times 6. 1.2 times 6, we can just think of this as 12 times 6, which is 72. And then we have one number to the right of the decimal, so our answer is going to move one place to the left of the decimal. So our answer is $7.20. A reminder, don't forget to download the HESI Test Prep app from the App Store or Google Play, where you'll find the homework and practice test for this lesson. Make sure you score at least 80% on the practice test before moving on to the next lesson. Thank you, I hope this was helpful, and I'll see you next time.